Elon Musk wants to build a city on Mars. Is that science fiction, or is it grounded in physics? This isn't a small idea, it's one of the biggest ideas humanity has ever considered. We are talking about taking our species, our culture, our very biology, and planting it on another world. A world that is cold, distant, seemingly hostile to life as we know it. The dream is epic, a testament to human ambition, but dreams are not enough. We need a vehicle, a plan. The key is a giant stainless steel rocket called Starship. Starship is the tool that could make a Martian city possible, designed to be big enough, cheap enough to carry massive cargo and people for a self-sustaining outpost. Think of it as a rocket, an interplanetary moving van, a cosmic Mayflower. Without Starship, the logistics of building anything on Mars would be impossible. It represents the bridge between Earthbound reality and a multi-planetary future. So how do we get from a blueprint on a screen to boots on red Martian soil? The answer is physics. Not the jargon-filled textbook physics, but simple, powerful principles of motion, energy, and survival. First, you have to get off the ground. Earth holds onto us with a powerful force called gravity. To escape it, you need to push back with an even greater force. This is what rockets do. They are engines of pure, controlled violence, throwing mass downward at incredible speed to propel themselves upward. This principle is called Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket works by expelling hot gas from its engines. The action is the gas being pushed down. The reaction is the rocket being pushed up towards the stars. It's a simple concept, but achieving it requires immense power. Starship is designed to be the most powerful rocket ever built. It uses over 30 engines, all firing at once to generate a staggering amount of thrust. The total upward push is around 17 million pounds or 7,500 metric tons. To put that in perspective, that's more than twice the power of the Saturn V rocket that took astronauts to the moon. Imagine the weight of about 4,000 cars, all pushing upward at the same time. This is the kind of brute force needed to lift not just a small capsule, but a massive spacecraft loaded with over 100 tons of cargo, the equivalent of about 10 school buses, all the way into orbit. Most of a rocket's weight at launch is not the rocket itself, or even its payload, it is fuel. For Starship, this means thousands of tons of liquid methane and liquid oxygen. The rocket is essentially a gigantic flying thermos bottle filled with supercooled propellants. To get its 100-ton payload into orbit, it has to burn through about 4,500 tons of this fuel. That means for every 1 pound of cargo you want to send to space, you need about 45 pounds of fuel just to get it off Earth. The physics of launch is a game of massive scales where the cost of fighting gravity is paid in tons of propellant. This is why reusability is so critical. In the past, we threw away our rockets after a single use. That would be like throwing away an airplane after one flight. Starship is designed to be fully and rapidly reusable. The booster that pushes it into the sky and the ship itself are both meant to land back on Earth, refuel, and fly again. By reusing the most expensive parts, the cost of each launch drops dramatically. This doesn't change the laws of physics, but it changes the economics. Once Starship is in Earth's orbit, the brute force part of the journey is over. The next phase is a long, quiet coast through the vast emptiness of space. Orbital mechanics govern this phase, the elegant cosmic dance of gravity. The spacecraft doesn't fly in a straight line. Instead, it follows a long, curving, Hohmann transfer orbit. It's the most fuel-efficient path between planets. A short engine burst pushes the ship into a new, larger orbit around the Sun, timed to intercept Mars months later. The key concept, delta V, a change in velocity. Every maneuver costs delta V, speeding up, slowing down, changing direction, and delta V costs fuel. The trip needs about 2.5 miles per second, or 4 kilometers per second. That push kicks the craft out of Earth's orbit, but Starship uses most fuel getting to orbit. It arrives nearly empty. So the plan: refuel in space. Launch multiple tanker starships. They rendezvous in orbit, dock, and transfer thousands of tons of liquid methane and oxygen. It's like a gas station in the sky. A complex robotic ballet hundreds of miles up at 17,500 mph. Arriving at Mars is just as hard, if not harder, than leaving Earth. Starship will approach the red planet at a blistering speed of about 17,000 miles per hour. It has to slow down and land safely, but Mars presents a unique and difficult challenge. Its atmosphere is very thin, less than 1% as dense as Earth's. This means there isn't much air to help you brake. On Earth, a returning capsule can rely on thick air to act like a giant air brake, shedding speed through friction. On Mars, the atmosphere is too thin for that to be enough, but it's just thick enough to create a massive amount of heat. Starship will perform the belly flop, turning sideways to fall through the Martian sky with its massive underside forward, maximizing drag and bleeding off speed. The bottom of the ship is covered in heat-resistant tiles designed to protect it from entry heating that reaches thousands of degrees. It's a delicate balance. Slow down using air, but not enough to burn up. A controlled fall, like skydiving a 16-story building. Even after the belly flop, it's still too fast to land. In the last few miles, Starship flips upright and reignites its powerful Raptor engines in a propulsive landing. The engines provide final braking, slowing from hundreds of miles per hour to a gentle touchdown. SpaceX lands Falcon 9 boosters on Earth, but doing it on Mars, 100 million miles away, with significant communication delay, is a new level of difficulty. Everything must be perfectly autonomous. Analyze terrain, adjust thrust, steer to a flat landing spot, all in minutes. There is no room for error. Miss ignition, or lose stability in Martian winds, and the result is catastrophic. Success is a soft touchdown. Failure, a very expensive crater. Once you've landed on Mars, the physics challenges have only just begun. Now you have to stay alive. Mars is not friendly. There is no breathable air. The atmosphere is 95% carbon dioxide. Temperatures can plunge to -200 Fahrenheit, -128 Celsius. And perhaps most dangerous of all, the surface is bombarded with deadly radiation, from the sun and from deep space. Without Earth's thick atmosphere and magnetic field, living on Mars means creating a completely artificial environment. A small bubble of Earth on a hostile world. The first physical requirement is energy. A Martian city needs power for life support, to make fuel, and to run equipment. The most likely source is solar. Thousands of panels must be deployed to capture faint Martian sunlight, about 40% of Earth's. At night and during planet-wide dust storms, the city would rely on batteries and other storage systems. Power is the foundation of survival. Next, life support. Humans need oxygen, water, and stable air pressure. Habitats must be pressurized, sealed containers. Oxygen can be made from Martian CO2. Moxie proved it. A city scales it up. Water will be mined from subsurface ice, then melted and purified. Survival also demands radiation shielding, bury habitats, use regolith as a natural shield. Building a city anywhere is a massive logistical challenge. On another planet, it's almost unimaginable. The physics isn't one ship, it's hundreds or thousands. A single Starship can carry about 100 tons of cargo. A city needs millions of tons. Early pioneers need habitats, power plants, water extractors, fuel production, greenhouses, tools, vehicles, spare parts. Every single screw, wire, and computer chip must be shipped from Earth. 1,000 people might require at least 1 million tons delivered to Mars. At 100 tons per flight, that's 10,000 successful landings. Launch windows open every 26 months. A Mars fleet launches in quick succession each window. In situ resource utilization is the core principle, live off the land. Water for drinking and oxygen for breathing. Split H2O into hydrogen and oxygen. Combine hydrogen with CO2 to make methane. CH4 and O2, Starship's propellants. Refuel on Mars, fly back, repeat. Transport becomes a loop, physically and economically plausible. While physics allows it, the path is filled with risks and unknowns. This is not guaranteed. A fleet making thousands of flights must be more reliable than any rocket in history, closer to an airliner. A single catastrophic failure with crew could set the program back years. Or end it. Long-term radiation and low gravity are harmful. ISS data shows bone and muscle loss. Months of transit followed by life at 38% Earth's gravity. We don't yet know lifelong impacts. Can people have healthy children on Mars? The biology is a massive open question. Martian dust is fine, abrasive, electrostatic. It sticks to everything, infiltrates mechanisms, clogs filters, damages seals, and may harm lungs. Global storms can block the sun for weeks, crippling solar and forcing survival on stored energy. Plans depend on mining ice and making fuel at scale. Models suggest ice exists, but only on the ground will we know accessibility. If water is harder to extract than expected, self-sufficiency could collapse. The city's success hinges on resources matching models. After the immense power, the cosmic distances, and profound risks, we return to our question. Can we really build a city on Mars? The physics says yes. No fundamental law blocks the path. The challenges are of engineering, scale, and will. We know rockets, we understand orbits, and we have credible plans to land and survive. Obstacles are formidable, but surmountable with technology, resources, and focused effort. If we succeed, the payoff transforms our species. For the first time, in 4 billion years, life moves to another planet, a backup for humanity, a planetary insurance policy. The effort ignites innovation in energy, recycling, agriculture, robotics, with benefits on Earth. It inspires a new generation and unifies us with a shared adventure. It lifts our perspective from local concerns to a grand cosmic vision. It would be the next great leap, securing our long-term future among the stars. When you look up at the night sky, you see countless stars and planets. For all of human history, we were confined to one planet. A city on Mars is a fundamental shift. It is the first concrete step from a species of Earth to a species of the cosmos. This isn't about planting a flag. It's about extending fragile tendrils of life beyond the cradle. The physics of Starship gives a plausible pathway. The journey is incredibly difficult. Force is immense. Distance is vast. Destination unforgiving. Every stage pushes limits. Violent launch. Fiery landing. Daily struggle for survival. 1,000 ways to fail. Engineering must be perfect. Resources available. Will sustain. Difficulty isn't impossibility. Mars forces a long view. Not the next election or quarter, but the next 1,000 years. The next million. What future do we want for our descendants? One point of failure, or multiple footholds across the solar system. A Martian city is a bet on resilience, expansion, and survival. We are explorers. It's in our DNA. Starship physics is today's vehicle for that impulse. Whether or not we see it completed, striving redefines what's possible. Final.